Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin the third and final application of derivatives of a function, and that is to calculate the maxima and minima. So suppose you have a function whose graph looks something like this. So it starts off at infinity, goes down to minus infinity, and this is how the graph looks in between. What is the maximum value of the function? At this point, it's infinity, right? We don't want it to be infinity, so let's say we'll restrict it between some domain. Let's say this is A, and let's say this point is B. So let's see how we are talking between A and B. Now, f does indeed have a maximum value. Y of x, it does indeed have a maximum value, and that is the value at A. So it is equal to y at A. What is the minimum value? This is y at B, right? But there are a few more points here that are special. Let's call this point C, D, E, and F. Now, points D and F are called, these two, the first ones are called global maximum and minimum value. The global maximum value of a function is the maximum possible value of the function within the region of interest. Between A and B is our region of interest. Y is greatest at x is equal to A, so this is the global maximum. Global minimum means the minimum possible value within the region of interest. That is the value at B. However, D and F are points which are called local maximas. Because within their own neighborhood, if you look at only this region, or if this is D, if you look at a small region near D, D is a maximum. Obviously, it is not the global maximum of the function because the value of the function at A is greater than it is at D. But within its neighborhood, within its local neighborhood, it is a maximum, or it is known as a maxima. Similarly, F is a maxima. C and E within their own neighborhoods are minimum value. See, within this neighborhood, C is the minimum value in E, and within this neighborhood, C is the minimum value. So they are called the local minimas. And given a function, say y is equal to x cubed minus 3x squared plus 9x minus 7, we can use the concepts of derivatives of the function to calculate the global maximum value, global minimum value, and local maximas and local minimas. So before that, let's put these maximum values in some formal definition. So let's say f is defined between A to B, or it doesn't need to be defined between A to B, it can be defined in a bigger region, but A to B is our region of interest. Then the point C is called the global maximum of f or of y of x. We often say y of x or f of x interchangeably. C is called the global maximum of f if f of c is greater than f of x for all x not equal to c between a and b. So the value of the function at c has to be greater than the value of the function at any other value between a and b. This says that x is between a and b, but it is not c. For c there will be an equality, right? So if f of c is greater than fx for all other x, then c is called the global maximum, and f of c is called the global maximum, the value of y, and c is called the point of maximum value. It is also sometimes called the point of global maximum value to distinguish it from local. So this is, let's say, our function. This is the region of interest. This will be the point C, and this will be f of c. F of c will be the global maximum value of f, and c will be the point where that maximum value occurs. Similarly, f of c is called the global minimum of f if f of c is less than f of x for all other x. That means for all x which are not c but which belong to a comma b. In this case, c is equal to a. I should have drawn a different figure. Let's say a figure like this. This is a, this is b. In that case, this would be f of c and this would be the point c if they are the maximum values. Right. Also, the maximum and the minimum together are called extremes. Which means if we say that it is a global extreme at f, that means it's either the maximum or the minimum. And all the points of extreme values are the points of maximum values or the points of minimum values. Right. So this is global maxima and global minima. Sometimes we talk about local maxima and local minima within their own region. So let's look at the definition for local maxima and local minima. Again, we'll assume f is defined, or the region of interest is a to b. Let's say the curve is something like this. Right. So C, D, E, F, G. Let's see. So f of c is called a local minima if, and now we are talking about the local minima, not the global minima. If f of c is greater than f of h, f of x for all x not equal to c between c plus h and c minus h. In fact, it's slightly different than this. F is called a local minima if there exists an h for which, if you can find a number h such that between c minus h and c plus h. Now this does not cover everything between a and b. If h is very very small, then this will cover points very near to c, right? So if between c minus h and c plus h, f of c is greater than all other f of x, if you can find such an x, which in this case you can find, but you won't be able to find such an x in this case. So if you can find such an h in this case, then f of c is called a local minima and c is called the point of local minima, or the point of, sorry, this is the maxima, I apologize. We'll talk about minima afterwards. So C is called the point of local maxima or the local maximum value. Similarly, let's do for minimum. F of C called local minima if there exists an h for which f of c is less than f of x for all x not equal to c but which belong to c minus h and c plus h. So this is the one difference between points you need to remember. You have global maximum and minimum points, which are the maximum or minimum possible values of the function in the whole region of interest, and then you have local maximum and minimum points, which are points in which the function's value is maximum or minimum. In this case, the minimum would be D and F within their neighborhood of interest. You don't need to check the whole region. If within their local neighborhood, this is where the word local comes from, if within their local neighborhood C or D or E are a maximum or a minimum value, they are called the local minima. And just like global maxima and global minima are together called extreme points, local maxima and local minima are together called critical points. So every critical point is either a point of local maximum value or a point of local minimum value. In this case, C would be called the point of local minimum value. And every extreme point is either a point of global maximum value or a global minimum value. Now this was the definition of maximas and minimas. Now let's look at how we can calculate them using the concept of derivatives. So for that we have a theorem. If f is defined in the region a comma b, then if C is a critical point, a critical point would be a local maxima or a local minima. So if f is defined in a region, then if you want a critical point, then either f dash of z is equal to 0 or f is not differentiable at C. I'll get to the second part, not differentiable, in a minute. Let's look at the first part first. If C is a point of local maxima, then it will look something like this. Now let's draw tangents to this. This is the tangent which has a slope which is some positive value. So the derivative f dash of x is positive here. This is also a point with the derivative positive, but it has a slightly smaller value tan theta because theta is now smaller. This has an even smaller value. At this point, at the point where it is at a maximum value, f dash of x, or in this case f dash of c, is equal to 0 because the line is parallel to the x-axis. We saw in the previous video of tangents and normals, points which have a derivative 0 have a slope 0, which means they have tangents which are parallel to the x-axis. And then you have this is some f dash x which is less than 0 because the angle it makes with the x-axis is greater than 90 degrees. And then you will have other tangents like this. So we can see that near a point of local maxima or at a point of local maxima, the derivative has to be 0. Similarly, if you have a local minima like this, even then, at the point of local minima, you will have a line which is parallel to the x-axis. So you will have f dash c is equal to 0. Right. So here f dash x is negative, it goes to 0, and here f dash of x is positive. If the line makes an acute angle with the positive x-axis, the slope is positive. If the line makes an obtuse angle with the positive x-axis, the slope is negative. So we can see that in critical points, either f dash c is 0 or the other point was f is not differentiable. Now in your course, you will mostly deal with differentiable functions, but just for the sake of completeness, it is possible that f is not differentiable yet a local maxima and minima. So look at a function like this. This function does have a local maxima at this point and it has a local minima at this point. But these functions are not differentiable because the left hand limits and the right hand limits are not the same. Right, you can look at the video of differentiability to understand that concept. Right, so non-differentiable functions can have maxima or minima, but you have a function which is differentiable, and remember sin x, cos x, tan x, all of them are differentiable. So if you have a function which is differentiable, then at a critical point, which is a local maxima or a local minima, the derivative of f will always be 0. Right, note that the opposite of this need not be true, which means if the derivative is 0, that does not mean it's a local maxima or a local minima. And the best example for that is a function like fx is equal to x cube. From that we get f dash of x is equal to 3x square, which is 0 at x is equal to 0. But this point is neither a maxima nor a minima because the graph of x cube looks something like this. right? So we can see that even though at the origin, at x is equal to 0, the slope is 0, this point is neither a maximum nor a minimum value, right? Minimas are like this, maximas are like this. But if you have something like this, still the slope is 0, but this is neither a maxima nor a minima. So the slope being 0 does not guarantee it's a maxima or minima, but if it is a maxima or minima, that means the slope has to be 0, or else it has to be non-differentiable. So our goal in this video was to be able to calculate the maximas and minimas of a function, and we are halfway there. Let's say we have a function y is equal to x cubed minus 3x, right? And we want to find the maximas and minimas of this function, right? So we'll just calculate dy by dx. That will be y dash of x, just like we were writing f dash x in the previous slide, which will be 3x squared minus 3. And we can see that y dash of x is equal to 0 at x is equal to 1 and at x is equal to minus 1. There are 2 points where it is 0. Now, what we know for sure is that this is either a maximum or minimum point, and this is either a maximum or minimum point. Actually, that's not true. There can be a third option, which we'll see in a minute. But the point is, we've known how to find out the maximas or the minimas, but we still haven't found out how to differentiate between the two. Okay, so in actuality, if you look at this function, at x is equal to 1, it will be a minima, and at x is equal to minus 1, it will be a maxima. So now we'll see that in a moment, we'll prove that, but right now that's what our goal is to calculate. We know that both of them have a slope 0, but how do we know which one is the maxima, which one is the minima? So within the graph itself, we can see a difference between the maxima and a minima. In fact, it's a difference which we've already seen a few minutes ago. So this is the minima, this is the maxima. I'll just draw the tangents again at points near the maximas or minimas, which is the local neighborhood of maximas or minimas. And let's just say I'll draw this as well, which was what we saw in the case of x cubed, which means the slope is 0 but neither a maxima nor a minima. So I'm just going to write y dash for dy by dx, and we'll see the directions of y dash or the signs of y dash. So here y dash is less than 0, because if you take a line like this, the angle it makes with the positive x-axis is greater than 90, and in the second quadrant tan theta is negative. So here y dash is less than 0. For this line also, y dash is less than 0. This is the line where y dash becomes 0. Now this is the point where y dash is greater than 0. Any point like this, any line like this, will have an acute angle with the positive x-axis, so tan theta will be positive. So we can see that in a maxima, in a minima, right now we're talking about the minima. In a minima, y dash is negative, then 0, and then positive. What happens in a maxima? Y dash is greater than 0 here, y dash becomes 0 here, and look at these lines which are here, y dash is less than 0 here. So y dash goes from positive to 0 to negative. And let's look at this point. This is negative, this is negative, this is y dash is equal to 0. These are points again where y dash is negative. So that's the third point where y dash goes from negative to 0 to negative. The second point is the maxima. And the third point is referred to as a point of inflection. Right. So in a maxima, the derivative goes from negative to 0 to positive. Sorry, in a minima, I apologize. Once again. In a minima, the derivative goes from negative to 0 to positive. For a maxima, the derivative goes from positive to 0 to negative. And for a point of inflection, it goes from negative to negative, or it can go from positive to positive, like in this case. Right. So, and remember, this is the immediate neighborhood. You could say, well, this is y dash is greater than 0, but it's less than 0 here. So if we count a big region around this point, you could say that it goes finally to negative again. But we are only talking about the immediate neighborhood. So these are the three definitions of maxima and minima and point of inflection, and these are how we can actually differentiate between them. If the derivative goes from negative to 0 to positive, it is called a minima. If the derivative goes from positive to 0 to negative, it is called a maxima. And if the derivative does not change sign, it is either negative both before and afterwards, or it is positive both before and afterwards. In that case, it is called the point of inflection. So let's look at the previous case. We saw y is equal to x cube minus 3x. From that we got dy by dx is equal to 3x squared minus 3. Right. Now, at this is 0, at x is equal to 1 and minus 1. Let's look at x is equal to 1. At x is equal to 1, y dash is equal to 0. What happens just before 1? What happens when x is 0.999? When x is 0.999, then 3x square minus 3 will be negative. And when x is just slightly greater than 1, that is 1.001, dy by dx is positive. So dy by dx is actually going from negative to 0 to positive as x goes from 0.99 to 1 to 1.01. Hence we know that x is equal to 1 is a minima. Similarly, at x is equal to minus 1, if x is slightly smaller than minus 1, then this term will be positive because x square will be slightly greater than 1. And if x is slightly greater than minus 1, this will be negative because x square will be slightly smaller than 1. So for the case of minus 1, y dash goes from positive to 0 to negative. So x is equal to 1 was the minima and x is equal to minus 1 is the maxima. In this case, there is no point of inflection, but if you look at y is equal to x cube, then dy by dx is equal to 3x squared. So we can see near 0, as x is positive but small, dy by dx is positive. As x is negative but small, dy by dx is still negative. So near x is equal to 0, the derivative goes from positive to 0 to positive, and positive to 0 to positive or negative to 0 to negative are called points of inflection. Right. Now we can actually put this in a slightly better format as well. So instead of looking at the maxima and minima for different functions and the directions and as they go from negative to 0 to positive or vice versa, we can look at the second derivatives. We know what the second derivative is. Y dash of x is dy by dx is the first derivative. Y double dash of x written as d2y by dx squared is d by dx of dy by dx, double derivative. And let's look at our function which we were looking at. Y is equal to x cube minus 3x, dy by dx will be 3x squared minus 3, d2y by dx squared, or the double derivative, will be the derivative of dy by dx, that will be 6x. Right. Now what is the derivative basically? So y dash of x is limit delta x goes to 0, y of x plus delta x minus y of x by delta x. Right. And from this we already saw in the video of tangents and normals, if y of x is an increasing function, then y dash x is positive. Right. Increasing implies y dash x greater than 0. Decreasing implies y dash x is less than 0. Constant implies y dash x is equal to 0. Now this is for y. So if y is increasing, y dash x is greater than 0. If y is decreasing, y dash x is less than 0. If y is constant, y dash x is equal to 0. Right. But we want y dash. Remember, if y dash goes from negative to 0 to positive, it's a minima. If y dash goes from positive to 0 to negative, maxima. And if y dash goes from negative to 0 to negative or positive to 0 to positive, It's the point of inflection. Right. So now what we did earlier for y and y dash, we'll do for y dash and y double dash. So listen to the words carefully. If y is an increasing function, then y dash x is greater than 0. So that means if y dash is an increasing function, that would mean y double dash of x is greater than 0, right? If y increases, y dash will be greater than 0. If y increases, the derivative of y will be positive. That means if y dash increases, the derivative of y dash will be positive. If y dash decreases, it means the derivative of y dash, which will be y double dash, will be negative. And if y dash is constant, that means y double dash of x is equal to 0. What we did here between y and y dash, we are doing here between y dash and y double dash. And we can see that if y dash goes from negative to 0 to positive, obviously y dash is increasing. And if y dash is increasing, y double dash is greater than 0. That means the condition for minima is y double dash greater than 0. The double derivative should be positive. Similarly, at a maxima, the derivative goes from positive to 0 to negative. That means the y dash is decreasing, which would mean y double dash is 0. So this means y double dash is 0. And at a point of inflection, y double dash is 0. Sorry, this means y dash is double dash is less than 0. This means y double dash is 0. Right. Now let's look at the case which we've been seeing so far. We found out that for x is equal to 1, it was a minima. For x is equal to minus 1, it was a maxima. But we can see that directly from this equation. When x is equal to 1, y double dash x is greater than 0, which means x is equal to 1 is a minima. When x is equal to minus 1, this is minus 6. So when x is minus 1, y double dash of x is less than 0, which means x is equal to minus 1 is a maxima. And then you have the point of inflection at which these two values are the same. Right. Let's look at this function in detail once more just to see it all. Y is equal to x cube minus 3x. dy by dx is equal to 3x squared minus 3 is equal to 0 at x is equal to 1 and minus 1. d2y by dx squared is equal to 6x. That means y double dash is greater than 0 at x is equal to 1. Y double dash x is less than 0 at x is equal to minus 1. Which means x is equal to 1 is and x is equal to minus 1. But our work is not done here. We still have one thing left. In the question we were asked, what is the global maximum and minimum value of this function? That's what we want, the maximum and minimum value of this function. So if we know the max value is minimum at 1, then what is the value? You simply put x is equal to 1. So minimum, and rather we should say local. The local minimum of y is y of 1, which is minus 2. Local maximum of y is y of minus 1, which is this will be minus 1 and this will be 3, so this will be 2. Right. Now let me show you how the graph for this function actually goes. What is the value at x is equal to 0? At x is equal to 0, I'll just draw the lines in a better way. At x is equal to 0, the value of y is 0. Right. As x goes to infinity, value of y goes to infinity. Right. So as x goes to infinity, value of y goes to infinity. As x goes to minus infinity, y also goes to minus infinity. Right. But at x is equal to 1, y is equal to minus 2, and x is equal to 2. X is equal to minus 1, y is equal to 2. So the graph of this function actually goes something like this. If as x goes to infinity, y also goes to infinity. As x goes to minus infinity, y goes to minus infinity. So if you were asked what is the global maximum value of this function, that is infinity. What is the global minimum value of this function? That is minus infinity. What is the local maximum value of this function? That is 2. And it happens at x is equal to minus 1. What is the local minimum value of this function? That is minus 2, which happens at x is equal to 1. How did we get that? We calculated dy by dx, and we know that dy by dx has to be 0 at all local maximum or minimum values. Then we found out that this is x is equal to 1 or minus 1, which are maximum or minimum values, or they could have been the point of inflection as well. Then we calculated the double derivative. If the double derivative is positive, it's a minima. If the double derivative is negative, it's a maxima. And if the double derivative happened to be 0, then it would be a point of inflection. This completes maximum and minima and hence application of derivatives. Thank you.